Yeah. So, today we shall do some other like we have done the film, and now we will do such a system like we have seen the flow through a pipe, right. If a fluid is flowing through that, we have found out, and with that Hagen-Paiseli's equations we developed, right. Now, if the situation is like that, in many cases you will see you have a double tube heat exchanger, right. So, you have a double tube heat exchanger. One fluid is flowing through this, so that you can find out with this Hagen-Paiseli. Another fluid, say that may be co-current or counter current depending on the situation, is flowing over this. So, this could be some medium by which is being heated. This could be that heating the thing which is being heated, and this could be another which is the medium which is to be this heating medium, right. So, if this is the heating medium and if this is to be heated, say this is milk and this is steam, right. So, in that case your of course, they will be insulated. In reality, that will be insulated, like here there will have one insulation, similarly here there will have one insulation. So, that is different, that is the engineering part, but what we are concerned is if this flow we can find out with Hagen-Paiseli, the same Hagen-Paiseli cannot be utilized for this kind of fluid, and in that case this is called flow through annular medium, right. In that case, if we know that flow through annular medium, how we can get it, then okay. So, flow through annular medium, this is the one which we are going to determine, right. Now, if you remember, in earlier cases we had taken the many cases horizontal. So, in this case let us also take it to be vertical, right. The difference between horizontal and vertical will be obviously the gravity. So, when gravity is also taken care of, and the gravity when it is taken care of, obviously that will come under the pressure force. So, gravity, the entire thing, whether it is again towards the gravity or away from the gravity, that depends on the flow of the fluid, right. So, in any case, let us take one such. Here you see we have neatly drawn that this is the one pipe, and this is another, this is the section of the pipe which is having annular flow, right. So, we are not concerned about the fluid which is flowing through this, but we are concerned about the fluid which is flowing through this annular place. So, this annulus flow or flow through annulus is in many cases are very useful, particularly for designing your designing engineering equipments, like say heating equipments, cooling equipments. In those cases, these heat exchangers, they are very useful. So, there you need to know the flow behavior, how flow behavior characteristics, how the flow is determined, how the velocity can be determined, what will be the momentum flux inside the system. So, those things if we want to determine, then we take this, right. So, we are taking then this as the annular flow, and in this let us take the at the center the axis and we have one radius, outer radius r, and inner radius a multiple of r, say kr, right. Obviously, this k from the physical understanding, it appears that k has to be less than 1, otherwise it will not be less than r, right. R is the outer and kr is the inner, right. So, if we take that inner and outer, of course, this arrow should have been here, right. This arrow is up to this, perhaps by some mistake it has gone up to that. So, it is from the inner wall, right. This is the thickness of the wall. So, if we take this, then we have to find out what is the velocity distribution in this annular space and what is the shear stress or momentum flux distribution in this, right. So, our this thing is coordinate system is r, z, r is the radial one, z is the vertical, and third one is the theta. So, this being cylindrical, so r theta z, that coordinate we are following, right. So, if we are following that r theta z coordinate, of course, here only one thing which we are saying, that r is this and z is the vertical and theta, that none other dimension is there. Now, we assume in the beginning there will be obviously some assumptions. So, those assumptions in that, first we say that the fluid is incompressible, right. Fluid is incompressible. That means density does not vary with pressure significantly, that we assume that this density remains constant, right. And then some other assumptions we assume, say the second one is flow is laminar. The moment flow is laminar, that is why this third dimension theta is coming out, going out, right. You remember we had this vertical cylinders. So, I am not taking the thickness, right, and this was our axis, and we had said this is to be kr, and we also said that this is to be r, right, and we have to find out what is the velocity profile. What is the velocity profile in this, and what is the stress profile in this, right. We said like this. Okay. So, K, R and R are the radii. So, flow is laminar, that is why the third dimension. So, when the flow is occurring, so it is like this, right. So, in this theta direction there is no rippling, no turbulence. So, they are having a streamline flow, that is why we are not keeping theta in this, right. Then there is no end effect, and the fluid is flowing between two vertical coaxial cylinders, right, with a laminar flow, and the vertical cylinders radii are kr and r, inner and outer radii respectively, right. And the laminar turbulent transition occurs in the neighborhood of somewhere 2000 to 4000, right, that we know that this is the transition zone between laminar and turbulence, right? And this, if we take a momentum balance in this, right, we can start with, as we said earlier, you remember that in many cases we will say that instead of doing every time from the beginning, doing all the balances, force balances, and using the governing equation, rate of momentum in minus rate of momentum out plus sum of the forces acting on it is equals to rate of momentum accumulation, then steady state, or even if it is not steady, then that unsteady del rho del t, or the variable that comes in as the time is not independent, time is rather in this case that property is not independent of time. So in that case you need to take, but in here we have said fluid is incompressible, flow is laminar and steady, right? Right, and we are finding out doing the momentum balance. So if we do momentum balance, and if we look back the past where we had done for the pipe flow, right? So we came to a point where we could rewrite that ddr of tau r tau r z that was equals to delta p over L times R. If you remember this, we in the pipe flow we had said that in many cases subsequently we may start from here, because other things remain same, because the flow by bulk flow is not coming into picture. Bulk flow, because it is steady, so bulk flow is cancelling out, so only remaining the molecular transport, and in that molecular transport if we do the mass balance, momentum balance, then that bulk flow terms they will go out, and remaining that molecular transport, that we will land up to this. So that is why we referred earlier and told also earlier specifically that in future we may start with this if required, right. So here also we are taking that as the starting point, that let this be already derived, ddr of r tau r z del p over L times R, right, and this del p we can also write as P in minus P out over L times R, right. Now here this P, as I said, the moment we are taking vertical, so depending on the flow, and if you remember that we said that the flow will be in the z direction. So this was our RZ, right. So it is in the vertical direction. So we can tell that pressure P is equal to, total pressure P is equals to P plus rho G and Z, right. That vertical pressure due to the gravity and the pressure which is for the flow, these two together will be causing the total pressure P, which we are taking it at this P in minus P out, right. Acting in opposite direction, the gravity forces, if it is going like this, no, so it is acting, this gravity is like that, so the total pressure required is P plus this rho Gz, so it is acting against the gravity force. So, it is acting against the gravity force. Okay. So, that means this P is equals to P plus rho g z, right. Now, if we integrate it, we get tau r z and rewrite. Of course, if we integrate and rewrite, so we had r tau r z delta p over this was r, so r square by 2l plus c, and on rewriting we can say r tau r z is equals to delta p by 2l into r plus c1 by r, right. So, this means that we have one equation where this constant C1 has to be found out, and to find out this constant C1 we need to know the boundary conditions. So, boundary conditions which will be, right, the boundary conditions. Now, one thing we can refer it back, that unlike this pipe flow where the boundary condition was very much defined means we could say that since, so if we take this is as the pipe and we could, and this is the axis, then we could say that velocity, this is the solid wall. So, this is where the velocity is 0 and this is where your velocity is maximum, right, and this is where the momentum flux is maximum and this is where the momentum flux was minimum. So, if we had plotted, we had seen that the plot of the momentum flux was like this, and this other one, the plot of the velocity was like this, right. So, if you remember that we had made like this, and the other way, sorry. So, it is the other way, this comes like this. So, this is minimum and the maximum is there, minimum is there. So, it was like this, like a K, right. So, this was like that, and in that case we knew that at the center the velocity is maximum and at the surface the velocity is minimum. This you knew, right. And but here, when we are talking here, since we have no such r, and that means here at r is equals to 0, V is V max, and at r is equals to r, V is equals to 0. So, this boundary was known, but here we do not know where at r is equals to what r, what is the velocity where it will be maximum. So, at which r the velocity will be maximum, that is not known. So, in order to solve this kind of problem, what is done? We are assuming an imaginary r, say lambda r, right, an imaginary r we are assuming, say lambda r, where this velocity becomes maximum, right. If this velocity becomes maximum at the point lambda r, then we can put the boundary, right. So, here we can say at r is equals to lambda r, this momentum flux will be 0, at r is equals to lambda r, momentum flux will be equals to 0, right. Similarly, obviously r is equals to lambda r, that time we will also will see that velocity becomes V max, right. But what is the value of lambda, that we do not know. We are assuming at a distance, at a radius where this lambda is equal to some value, and that we have to determine. So, in order to find out this value of C1, let us now say that tau r z, that momentum flux is 0 at r is equals to lambda r, right. So, if that be true, then C1 becomes equals to minus delta p, right, into lambda r square, lambda r square divided by 2L, right. So, this lambda r, because this is 0 equals to delta p over 2L plus C1 by r. So, C1 becomes equals to delta p minus by 2L r square, right. So, this r we have put as lambda r square, and C1 value of C1 is like that. Then we can now say that boundary condition we have already said. So, then we can now say tau r z, this is equals to delta p, right, into by delta p by 2L into r. If we can write as r as common, then r by r, this minus lambda square capital R by small r, this on simplification we can write, right. So, tau r z we can write because substituting the value of C1 into this and then taking common delta v by 2L into r, then we can write this delta p by 2L r times r by r minus lambda square capital R by small r, right. So, if this is tau r z, then we can also say this tau r z is defined as tau r z is equals to this minus mu d v z dr, right. So, dvz dr, if that is there, then we can substitute this dvz dr is equals to this negative goes there, right, and we can write that this is equals to minus delta p by 2 mu L into r by r minus lambda square to r by r this, right. So, this is what we can write in terms of dvz. Now, integrating this dvz, we can say that vz, this is equal to delta p, we had minus delta p r by 2 mu L. So, this was there. So, on first this integration will come. So, it is that r if we take out and then rearrange, then we can say this is delta p by 4 mu L, right, times r square, r by r whole square minus 2 lambda square ln r by r plus C2, right. This is the second, right. Okay, this C2 here we can write that is equals C2, right. So, then if we substitute the boundary conditions, boundary condition 1 is at r is equals to kr, at r is equals to kr, we have Vz, or at r is equals to kr, we have Vz is equals to 0, right, and also at r is equals to r, we have Vz is equals to 0, right. This too, because there if you remember, so we had this at r is equals to r and r is equals to k, because that is the oval. So, this is the solid oval. So, where our fluid is getting clinged and this Vz becomes equals to 0. So, that boundary condition if we put and substitute this boundary condition into C2, we can write that 0 is equals to delta p over 4 mu L r square with a negative into 1 plus C2, and from there we can find out, C2 is equals to minus 1 and 2 lambda square is equals to 1 minus k square divided by ln of 1 by k. So, we find out the value of lambda, is equals to 1 minus k square divided by ln of 1 by k, right, this half, right, into, rather this is half and this to the power of again half, right, that is the value of lambda. So, if we know C2 and then lambda, then we can say that tau rz is now becoming equal to delta p over 2L into R is R by R, right, minus 1 minus k square divided by 2 ln of 1 by k, right, into 1 by or R by capital R. This is tau rz and Vz is equals to delta p divided by 2L or 4 mu L, rather delta Tp divided by 4 mu L to R square into 1 minus R by R whole square, right, plus 1 minus k square over ln of 1 by k, right, times ln of R by R. So, this is the velocity distribution and this is the momentum flux distribution, right. Now, here we have to find out, okay, in many cases, in earlier cases also, you have seen that we can determine this velocity profile and shear stress profile, and based on the relations we obtain, then we can substitute, we can substantiate whether our development is correct or not by putting some conditions. So that we will do in the next class, because this class time is over. Thank you.